Hi, I know it's been a long time since my last video, and I don't really have an excuse aside from starting 5 new projects every week then finishing none. There's always this part in my brain that says no me gusta and makes me lose my hyperfixation on a project because it makes me feel like no one will be interested on it nor it will bring me anywhere. But sometimes you have to force yourself into working with your projects. If you're seeing this video, it means that after this many times of forcing myself to work on this, I finally finished it. Okay, now for the good stuff. I wanted to kinda rework my first video, which explains what does ray tracing do. But does it? You see, we will never stop learning new things. North Americans learned that you shouldn't stare at an eclipse with the naked eye. Irresponsible parents learned that letting their underage child play VR chat unsupervised will cause severe psychological damage and will get the kid in big trouble. And I learned more about ray tracing. And so the new knowledge I got about this shows that I need to make a couple of corrections on that video. So then, first, but not second,
this rendering method is often used for photorealistic renders.
Even though it is true that photorealistic renders usually involve simulating light rays as in real life, ray tracing is better defined as rendering shapes using physics, also known as raycasting or intersecting.
Once Alex hits a surface, it will bounce or reflect depending on the normal of the triangle it hit.
Once you found the object the ray hit from the camera, you already did ray tracing. It doesn't actually need to bounce and stuff. When you bounce the rays, you're doing path tracing, which is a method that uses ray tracing recursively, but it isn't by itself. I will elaborate later.
Before being projected again, it will take the output color from the material and then get multiplied by the starting one, in this case white.
In here, I'm already explaining path tracing. I want to point out that the starting color of a path tracing ray will always be white.
After the last bounce, Alex will be assigned the color that has resulted with all those multiplication.
Damn. This is a dangerous one. You might have realized I have a memory span lower than a hydrogen 7 atom, and sometimes I correct myself too late. If a ray has intersected with a light, its color will be the surface color it hit multiplied by the color of the light. If it didn't hit, it can be either the environment or 0 in case there is no environment. But if it reached its maximum bounce amount and it hasn't found any light source or it hasn't reached the environment, it will be discarded and won't return any color. I did explain this, but as I said, I explained it too late.
Now repeat this process 1920 by 1080 times to get one sample. This is the result.
I feel like pointing out that the result can vary depending on how you want the surface to behave. In this case, it behaves as a metallic surface with no roughness whatsoever.
You can do that by adding a random value between -1 and 1. This can be done with sines and cosines of other sines and cosines of a seed. Adding
Oh, okay, that one keeps me up at night. That's not something I get Nerd's Night for, that's something I get nuclear bombed on. This will work, but at the same time it's dangerous, because you cannot guarantee that the ray won't bounce at a physically impossible direction at high values. But gladly, a big brain shaded depth showed me a formula that can deviate the bounce direction inside an hemisphere. Big credits to Pema for being so bonkers. You can find it at GitHub in the description.
Also, before continuing, I'd like to show this extremely beautiful piece of art a great friend of mine did. Here is her social media. She is an amazing artist.
Unrelated, but look how cute this is. I want to credit Mary again because I still love this piece of art so very much. The links are also in the description. Go buy from her, just commission her, she deserves it. And after that, I don't need to correct much else. So now let's Stereo from the theater explain ray tracing to you. Again, we're going to start from 0. Well, not actually 0, but 2 gradients. If you've been on Shader Toy, you might have been amazed at how many incredible shaders start from just these 2 coordinates. It's not strange to think about it when you realize that every pixel has its own value, which is never repeated in any other part of the screen. Now, how do you make a ray? I mean, it's not something that exists by itself. These supposed rays are just photons that move around and change the state depending on the molecules around them. Do we have to simulate that? Yes. While physics can be complex, by only knowing the most important values for our ray, we can already do ray tracing. The values are where the ray is and where is it going, commonly known as ray origin and ray direction. What ray tracing does is calculating the distance between that ray origin and the point in the surface that it will hit if it traveled towards its direction. Once you have the distance, if you have set the ray origin by the direction it travels towards, scaled by that distance, you'll get the position of the surface. Obviously, we won't get anywhere without knowing what direction it's the surface looking at, so we will have to calculate the normal. Unfortunately, doing so is a bit tricky. Don't worry though. Or do? Thanks to Inigo Quiles, the shader artist of all time, guessing a ray trace surface normals doesn't need to consist of repeating the trace twice to get a not so precise value of it. Now we have 2 vectors, but before we start tracing, let's just add 3 more values that will be useful for our ray tracer. A float for depth testing, a boolean to know if the ray hit a surface or not, and an integer to give every surface a unique identifier. Now we can start tracing, so okay. How do we start? As I said, we need 2 vectors, the origin and the direction. The origin is simple, just the position of your view. The direction is a bit more complex. We can set it to face towards the x-axis, but if it faces a uniform direction, it will be as if you had a camera with no field of view, because all the rays will go towards the same direction. To solve that, we make use of the coordinates that the shader provides us. We subtract 0.5 to the coordinates, so the center of the screen is 0, and then we can shift the direction depending on how far from the center the ray is by adding the value to the ray direction. To regulate the shift, we only need to multiply the coordinates by a factor, where 0 means there's no field of view, and the higher it is, the more field of view it will have. If you didn't know, ray tracing is not limited to triangles only. There is a couple of primitives we can do to reduce our needed triangle count to trace. And I want to thank again Inigo Quiles for his work in creating formulas to intersect many shapes. Let's start with the most simple intersection you can do. Planes. This intersection can be useful to do infinitely large surfaces such as water. The input parameters for all functions will always be the ray origin, ray direction, and the ray we want to write to. For the plane function, we will add a float tree for its position. The formula to get the distance is simply the ray direction's y-axis divided by a y-axis of the sum between the ray origin and the position of the plane. It doesn't need to be specifically the y-axis, just keep in mind both need to be the same one. Before writing the data to the ray, check if the depth is higher or equal to 0, otherwise don't write, because that will mean that it didn't intersect. Another check will be comparing if the depth of the plane is lower than the current survey's depth, basically depth testing. With this, we can start writing to our ray. The position is simply the origin plus the direction multiplied by the distance, as said before. The normal is simply the axis you calculated for the distance. In my case, my plane is on the positive y, then y it will be. Then we tell the ray that we intersected it. We put the distance that we calculated as the depth, and finally we assign the intersection's index. If you want to make the plane non-infinite, you can cut it however you want. You can add a float to as a parameter for the scale of the plane, calculate the wall position before assigning it to the ray, then get the absolute of the parallel axis of the plane, minus the wall position. If this vector is lower than half of the scale, it means that the ray intersected it. You can also scale it as a circle. It's simply having a float as an input parameter for the radius, getting the length of the wall position subtracted by the plane's position, then if the length is lower than the radius, intersect it. You can also do that with textures and such, but I think I'm infiniting too much already. So let's go to the next shape, spheres. If you didn't know, the perfect sphere is possible, and it's only one intersection away from you. No ray marching nor million polygon meshes, just one trace and you got a pixel perfect sphere. Start with the 3 main input parameters as always, and 2 extra parameters. a float tree for the sphere's position, and a float for its radius. The formula works by subtracting the sphere's position from the ray origin. That gives the position that the sphere is from the camera. Next, calculate the dot product between this vector and the ray direction. This draws the depth of a sphere between the camera and the object. After that, get the distance of the previous position by getting the dot product of the vector with itself. Then, if we subtract it by the radius, we will get the distance to the closest point to the sphere. Now, if we get the distance that we calculated previously, raise it to the power of 2, just like the others, and subtract it by the distance to the closest point, we will get the gradient of the sphere. And the only thing left to do is get the square root of this gradient to correct it into a sphere, then subtract it by the radial distance to the sphere's center. Now we got the depth finally. Now there are 2 checks we have to do before finishing the function. 1. Did it intersect with the sphere? That's true if the sphere's gradient is greater or equal to 0. 2. Is the sphere behind you? You will see this issue many times. When you render a shape, a copy of it will be calculated mirrored to the camera. Well, its difference is that it has a negative depth, making it as easy as doing a single check to remove it. We can finally write the data to our ray. As always, the position of the ray origin plus the ray direction multiplied by the depth. We indicate that the ray intersected, assign the ID, set the depth, and to calculate the normal of the shape, you can simply subtract the world position by the sphere's position and normalize it, because if you didn't know, if any vector has a length of 1, it will shape a sphere from the center of whatever space you're calculating it. That's why we only need the position coordinates of spheres from its center. Cubes. This one contains 3 plane intersections, 1 for each axis, from which only 3 will be seen. That's because you will never see more than 3 sides on a cube, unless your field of view is embedded. That's not our case. The function will have 2 additional parameters, a float tree for the position and another float tree for its size. First, we get the object's position from the origin by subtracting the ray origin from the cube's position. We will also multiply the size by half to convert it from a diameter to a radius, unless you want to use it as a radius. Before calculating the distance, multiply the size by the sign of the ray direction. That way we will always render the face that's closest or furthest from the origin. After that, we get the depth of the x, y, and z axis, offset by its corresponding size. Since it's just a plane function on all 3 axes, we can write it on a single line. We will do the same, but this time the offset will be negative. Now we have 3 intersections that will always appear as a backwards cube and 3 other intersections that will always appear as a normal cube. How do we convert them into a single cube? For the backwards cube, we get the minimum of the 3 axes. This will return the depth of an infinitely large backwards cube. For the normal cube, we get the maximum value of all 3 axes. If you couldn't tell, by subtracting the normal cube by the backwards cube, we can get a positive value where the cube is supposed to be and a negative value where it didn't intersect. If the normal cube is higher than the backwards cube, we intersect it with this shape. The depth is a normal cube, unless you want the cube to be embedded. The position is calculated the same way as all other functions, and the normal is calculated by getting which axis is the lowest from the normal cube's planes. If x is lower than the other 2 axes, the normal is x. If y is lower than the other 2 axes, it's y. And the same with z. It's kind of like the minimum operations we did before, but getting the comparison result instead. Then, depending on the ray direction, it will be negative or not. So multiply by the negative sign of the ray direction. Okay, that's cool and all, but what's the cool, ultra-realistic lighting stuff? In a minute. Let's do an example with what we learned. And what better example for 3D graphics than the kernel box? The kernel box consists of 3 walls, a floor, and a ceiling, with the left and right walls being red and green, respectively. The green one can be blue if you want to. The ceiling also has a square light, which won't work for now. Let's set up our functions first. Put as many permitted functions as you want, most importantly the plane function, which we will need to build the kernel box. You can have the functions on the shader itself or keep them in order on a different file. Before drawing the funny rays, we need to get something from our vertices, and that is the wall space position. Simply add a float tree for that vector on the vertex to fragment structure, and on the vertex shaded, assign it by the object to wall matrix multiplied by the vertex position. This multiplication, as the matrix name says, converts the vertex position from local space to wall space. we start the fragment shaded by getting the ray origin and direction. We will get the origin from a built-in variable named _wall space camera path, which, as its name suggests, is the position of the view that's currently rendering the shader. The direction will be the direction of our view. To get that, we subtract the camera position by the wall position vector we added in the vertex fragment structure. This gives us the distance a vertex is from the camera, and if we normalize it, we get a vector that represents the direction the pixels are facing at, which is the view direction, or right direction in this case. Note, if the ray origin is the camera position, the objects will be rendered at the wall 0. If you want it to be on the same position of the object you're rendering on, you have to add it to the wall position of the object, which you can easily extract from the object to wall matrix by getting the last axis of the 3 first vectors in the matrix. I write it as unity underscore object to wall underscore 14 underscore 24 underscore 34. Anyways, back to info dumping. Now we create a ray that will render the box. All values need to be initialized manually before using the structure. So let's do that. The position of normal is a value that the functions will return. We don't need to assign any special value to it, so it will be 0. The depth will be the maximum distance we want the ray to travel. I will make it 1000 because why not? Next, the value that tells if the ray hit an object or not. This value will start as false. And last, the ID will start as -1, since we know that no object will write this number. Now, how will we structure our kernel box? We will need 3 walls, 1 floor, 1 ceiling with a square light and anything inside of it. It can be a sphere or a box or another sphere or a couple of capsules. You can add anything inside it. First, the walls. The front one will face towards the negative Z axis, positioned at Z 0.1 with a width and height of 0.2. To check if the wall is rendering correctly, we will return the head value from the ray. If you did everything correctly, your material should look like this. Now, we will add another plane that faces -x at x 0.1, also with a width and height of 0.2. Let's do the same with another plane facing x at x minus 0.1, the floor plane facing y at y minus 0.y, and finally the ceiling facing -y at y 0.1. We built a base of a 20 cm kernel box. You might have noticed that I didn't add the ceiling light. That's because it won't be able to provide lighting for now, unless we use linearly transformed cosines, also known as LDCs, but that's something for another day. Lastly, we will add whatever we want inside. In my case, I add 2 spheres and a rectangle. If you find it confusing to position an object inside this completely white structure, you can return any value, such as the normal. That way, there's a greater color difference between shapes. Did you finish your shapes? Great! You finished your ray tracer. Now, all these intersection functions we wrote, we will pack them on a function because we will reuse it more than once. The function will get the ray origin and direction, the maximum depth, and an identifier to make sure a shape doesn't intersect with itself. Where the ray is initialized, the depth will be that input value, and for each intersection, we will check if the already written ID doesn't match with its own ID. To render all shapes, that value just needs to be -1. And after doing all of this, the function will return the ray that we rendered. Now here's the fun stuff. First, add this function to where the intersections were before. With this data, we're going to render PVR lighting. First, the color. Remember how each shape has an identifier? Let's put that to use. Create an array of fixed tree that will contain the color of each shape, and the ID that the ray returns will be the index of that array. So 0 is the front wall, which is white. 1 is the right wall, which will be green. 2 the left one, red. 3 the floor, white. 4 the ceiling, also white. And the shapes inside the box can be whatever color you want. Now all we need to do is create a flow tree that will be the color being that array with the ray's ID as the index. Now, lighting, directional lighting. To calculate the lighting of a directional light, we only need 2 things, the normals and the direction of the light, which can be any value as long as it's normalized afterwards. The function for it is the dot product between the normal and the light direction, saturated because the dark zone has negative values and we don't want that. Multiply this value by whatever color the light has and you finish your directional light. Move these lines to a new function where you input the ray, the light direction, and the light color. Then return a flow tree containing the light information and frame it into your wall. Be proud of your creation. Points. Point lights don't have a direction but a position, so we have to do an extra step before calculating the lighting. Subtract the wall position by the light's position, then normalize it. Now you can calculate the dot product between that vector and the normal. Saturate it, then multiply by the light color to get the light value. But wait, there's something more, and it's attenuation. The light density fades out the further away it is from the source. One way to calculate the attenuation is by getting the distance between the light and the wall position divided by the radius that this light will cover, then getting the reciprocal of this value plus 1. If you don't know what a reciprocal gradient is, it's simply 1 divided by a value. This value shouldn't reach 0 or else it will cause infinite values. And let me tell you, this is my favorite type of gradient. It looks beautiful. Now you have the light attenuation. The last thing you need to do is multiply the light result by this value and you're done. Now just move it as a new function with the input parameters being the ray and light position, the light color, and its radius. Frame it into your wall too. To apply all the lights, you only need to add them together and multiply them by the object's color we calculated previously. You thought I finished the lighting, you foolish being. Let me introduce you to shadows. This is actually very simple, just think about it. We know the wall position of the surfaces and where a light source is. If we trace the rays from their current positions towards the light, we can get the shadows by knowing if the ray has hit an object. Shadows can be applied to the light result by just multiplying by the negation of that heat volume. Now, how do I apply it to the different light types? For directional light, just create a new ray just like before and trace the scenes with the ray origin being the wall position which is traced and the direction being the directional light's direction. If it didn't hit an object, it means it has light. If not, too bad. To the shadow realm you go. Point lights are pretty much the same. The light duration is the same thing that we calculate on the lighting function, but negative. But this is a very important step to take before tracing. We have to avoid wrong ray hits, which are hits that happen after the ray has already reached the light. The solution is as simple as limiting the ray depth to the length between the ray origin and the light position. Now the ray won't intersect with objects further away than expected. And this is how you apply simple real-time lights to a ray tracer. The shadows are optional, but it's still nice to have them when you can just re-render all the objects in the same pass. That's it for lighting. Okay, alright. I will teach you how to do path tracing. A big warning, before doing anything, path traces are very heavy. Barely any game makes use of it. A renderer does ray tracing by getting the distance from an origin, facing a direction to an object. This is ray tracing. Now, if we want to know how the surface gets affected by its surroundings and its material, we have to redraw the rays from the surface, and depending on the material, the ray will move towards a certain direction. If it's smooth, it will reflect, and if it's rough, it will move towards a random direction. But which one? That's where path tracing becomes crazy expensive, since rough surfaces have a microscopic distortions, also known as microfacets. We receive an average of many rays at once, and by many I mean thousands if not nearly 1,000,000 rays per second. If our eye receptors could somehow only receive a single photon, everything will look very noisy. The same way your eyes are slightly noisy in the dark, but way more noticeable. And that brings us to the reason why path traces are so heavy. Each pixel is a receptor, but it's only able to receive one ray per sample, instead of the thousands our eyes receive. So if we render a rough surface, we will need to trace the rays multiple times towards different directions, thousands of times. Now, with that cleared, let's do a path tracing. And do our PBR shading lines and leave the first trace only. And now we can add the ceiling light, because we will need it. Go to the tracing function and add a plane intersection facing at -y with a size of 0.05 on both x and y axis, at height 0.099, just a bit below the ceiling so it doesn't z-fight. Now that we added the new shape, we have to increase the number of colors on the array by 1 and add the ceiling light's color, which is white. Now to do a test. We will create a new ray and trace the objects with the ray origin being the wall position of our objects and the ray direction being the normal. This is the normal result. Now, if we get the reflection vector from our view using the reflect function with the input parameters being the ray direction of our camera and the surface normal, we get a sharp reflective surface. Let's do one more step, get our new ray's ID and get the color from that value. If it didn't hit, this color will be 0 or black. Multiply this by the color of the first ray we got, and you got a metallic surface. Looks pretty clean, right? Now you see that it looks pretty strange too. That's because we're treating all surfaces as if they emitted white light. To keep things in order, we will modify our ray structure so that it contains two new values. First, a fixed ray that will contain the ray's color, and second, another fixed ray containing the light of the ray. In the trace function, the ray's color will be initialized as white and the light as black. After tracing all the shapes, if it hit a surface, we will assign the color of the ray as the color array and with the index being its ID, just like before. Otherwise, it will be 0 because right now we have no environment in our path tracing scene. The light value will come from a new float tree array, similar to the other one. Since our only light source is the ceiling light, all light values will be black, except for this one, which will emit white light. So if the ray hit a surface, also assign the light value as this array with the index being the same as the colors. Check if the ray is written correctly. Ray color and ray lighting. Looks fine. And now we will do something important. Apply roughness to the surface. We will use this function. It inputs the direction you want to shift, a seed, and the coordinates, which we will use to give a unique seed to each pixel. Its output will replace the ray direction. First the normal, then any number you want, then the coordinates. It can be any vector, the vertex position or view direction. In my case it will be the pixel position, which is the vector from the vertex to fragment structure that assigns SB_position. Now everything looks very noisy. Let's output the ray light instead of the color. Do you notice how it starts to look a bit more accurate? Let's do something. Put it inside a for loop, with the seed being the iterator variable, then create a float tree before it for the result, with its initial value being black, and every iteration add the ray's light. After this, return the result divided by the iteration count you put in the for loop. That looks more realistic. That's just the first part of your path tracer. Now you have to multiply the addition you do on the result by the ray color. After the loop, remove the return and directly divide the result by the iteration count. After that, multiply the result by the first ray's color, and then add its light. Pretty neat. If you're currently doing this, you might have noticed that your GPU is struggling if your path tracer is covering a high pixel count, or if you put a very high iteration count. Let's make it worse. Now we're going to apply bounces. It might sound complicated, but in reality it's as simple as putting the new trace inside another for loop that will iterate for every bounce plus 1. Outside of it, we will initialize a new ray with the first ray's values, and trace using the new ray's data. We will create a fixed tree for the ray's current color, with its starting value being white, and another for the resulting light, with its starting value being black. We will also add the bounce iterator to the trace seed to make sure it follows a random path. Every time it bounces, we will add the ray's current color multiplied by the ray's light to the resultant light, and afterwards we will multiply the color by the ray's color. After doing all the bounces, we return the resultant light. Let's start with 1 sample and 0 bounces. First, increase the bounces to 4. Then increase the samples to 32. And finally, you did a path tracing. You can play with it, do wacky stuff with it, make the seed vary with time so it's more recognizable, but your GPU might be crying already. That's why rendering path tracing takes seconds per frame instead of frames per second. The traces are distributed by CPU or GPU update cycles. If you thought I talked too much, I'm sorry. It will happen again. But for now, I hope this taught you something. Now go have fun, make your own super cool realistic renderers, or brag to your friends about your pixel perfect super smooth ray tracing balls, or just do anything. In the future, hopefully, I will teach you more advanced stuff about path tracing. If you want to see a cool use for a ray tracer, check out my experimental world, where you can pick up random objects and generate a light map with the click of a button. Also, the Jupiter you see in the sky is a real scale ray trace sphere. So yeah, thank you very much for staying here with my info dumping, and I hope you learned a lot with it.